In this video, we're going to solve triangles that require us to make use of the law of sines, but in the ambiguous case. So remember, for all uses of the law of sines and law of cosines, there's only one scenario that results in this ambiguous situation. All other scenarios, the triangle is completely unique. You just use the formula and get the values of the triangle, the unknown values. There's only one scenario where there's ambiguity, where you can potentially have two triangles that satisfy the given criteria, maybe just one triangle, maybe it works out that way, or perhaps there's not even a triangle that exists. A triangle can't be created using with the information that's given. And so that scenario is when you're given two side lengths and an angle. However, the angle is not included between the side lengths. And the way you see that you have an angle that's not included between the side lengths is you look to see, is one of the side lengths you have opposite of the angle you have? And we can see that it is, because based on the labeling convention for triangles, we have angle A, and we have the side length opposite of angle A. And then we have another side length, so we know we have the side-side angle case. This is the ambiguous case, which involves the law of sines. There is no ambiguous case with the law of cosines. The ambiguous case, you're dealing with the law of sines. Okay, so to answer this question, what we want to do is, it's saying solve each triangle. And so what that means is that if it's the case where there's no triangle that's possible, we want to state no solution, no triangle possible. If it's the case where one triangle is possible, we want to draw that triangle and put all of its side lengths and angles, and that's the final answer. If it's the case where two triangles are possible, we want to draw both triangles and put all of both the triangle, the side lengths and angles of both of the triangles, and say that, okay, here's the two possibilities based on what we were given. Okay, now, so as we talked about in this section, the first thing we do is we look and see, is the angle that we know acute or obtuse? So we see it's acute. So there's with the ambiguous case of the law of sines, there's 6 scenarios. You're going to have one of 6 scenarios. So now that, since we see that the angle is acute, that narrows it down to 4 scenarios. All right. Now, the next thing we do is we compare the length of the side opposite the angle to the side, you could say this is adjacent to the angle, and we see which one's larger. Well, the side opposite is larger than the adjacent side. Okay, and so that narrows it down to one case. That takes, because of the 4 acute angle cases, 3 of them involved the side opposite being shorter than the adjacent side, but there was only one case where the opposite side was greater than or equal to the adjacent side. So we found that case. Now, you know, you can go and bring up the table. Here's the table. You can go bring this up and reference it. They give you do you have an acute or obtuse angle, and then is the side length opposite the main angle greater than or less than? It tells you the criteria, so you can find what criteria you have. But we can draw this out as we talked about in the textbook section. So here's the side length that we don't know. Okay. Now, and here's the angle that we do know, and we'll put it at approximately 42 degrees, something like that. Okay. So this is side length. This is the angle A that we know, and this is the adjacent side length B. And now the side length that's opposite of this, so this length can be anything, and the side length opposite of this, so it's going to be, looks like about almost twice the length of this. So now this is on a hinge, right? We try not to change this length. This is on a hinge, and so because this angle that we're attached to doesn't matter, and so we just rotate this until we're all the way out here, even with this, because this length, you can make whatever you want. Okay, and we know that there's only one triangle possible in this case, because you can't, this orientation here is fixed. We made this line horizontal. This is side length C, angle C. We made this horizontal, and this angle is fixed. We specified this angle, so we can't move the orientation of this side length. It has to stay horizontal. So we can't, there's no way we could like continue to rotate side length A and still have a triangle. There's only one spot here where we can make a triangle. We know this isn't the two triangle case. And we can validate that, right? So we don't have an obtuse angle. We have an acute angle. But the side length opposite the angle is greater than or equal to the side length, the adjacent side length. Well, that's not the case here. That's not the case here. It's A is equal to H. H is less than B. And that's not the case here. A is less than B. So we know we're here. There's one angle. And we drew it out, and that's what we have, right? Now, okay. So next, what we're going to do is apply the law of sines. And for the ambiguous case, every time you apply the law of sines, you're going to end up with sine of B is equal to something. That's just a natural result of how this is set up. So we start off with sine of 42.5 degrees over side length A is 15.6. That's equal to, and then we need to use sine of B because we only know side length B. We don't know side length C. So sine of B, we don't know B, but we know side length B, 8.14. So solving for sine of B, okay, all over 15.6. Okay. So we know that we expect to get a value between 1 and, well, a positive value, something between 0 and 1. So for the sine of B. And there we go. Okay. Now we can take the inverse sine of both sides of this to get the B out. So B is equal to carry all those digits, 20.6415 degrees. But we introduced the inverse sine to this problem, so we need to consider the general case of what other angles, when you take their sine, do you get this value? Well, okay, we know we have sine is positive in the first and second quadrants, so what angle in the second quadrant is going to have this as a reference angle? Okay, so these are the two possibilities, these two angles. But we know that this is the case where we only have one triangle. There's not going to be two possibilities. And so what we talked about in the previous video going through this section was that what's going to happen for this case is that if you add this possibility to the angle that you're given, right? We can't have this as an angle. That's greater than 180. There's no way. So this is not a possibility. So the only option is B is 20.6 degrees. That's the only option. Okay, so now we've got angle A, angle B, side length A, side length B. We can go ahead and get angle C. So let me take this, add that to 42.5, and then 180 minus this. 116.9 is angle C. Okay, now we just need side length C. We could use the law of sines again. So side length C over is equal to, and let's go ahead and use, since we're given angle A and side length A, let's use those to avoid rounding errors. So we've got 15.6 over sine of 42.5. Okay, so side length C is going to be equal to, we can see cross multiplying 15.6 sine of and then over sine of 42.5 degrees. So let's see. Let's see if I can pull some of these values straight from the calculator. So 15.6 times sine of, now where's that angle? Right here. There we go. See, it pulls all the digits. Okay. Divided by sine of 42.5. 20.6 feet. And there we go. We've got, we were given these parameters for the two side lengths and an angle of a triangle. And what we found is there's only one triangle that you can make that corresponds to these values. And that triangle has the other side length is C, and the other two angles are B, these two. Okay, same idea. We're given three values for some side length angle combination for a triangle, and we're asked to solve the triangle. So we see we have two side lengths and an angle. And so the first thing that would come to mind is maybe we have side, angle, side, and we could use the law of cosines. You know, you'd rather not have to deal with the ambiguous case. You'd rather just deal with the nice, straightforward cases of the non-ambiguous law of sines or the law of cosines. But we can see that, well, one of our side lengths that we have is opposite the angle that we have, so we know it's the side-side angle case, ambiguous case of the law of sines. Okay, so we know that coming out of this, with these parameters, there might be no triangle that's possible. There still might be just one triangle that's possible, or it could be that there's two triangles that are possible. Okay, so we start off by saying, okay, the angle that we have, is it acute or is it obtuse? It's acute. So there's six cases, possible cases that come out of this, the ambiguous case of the law of sines. We've just eliminated two because we see we have an acute angle, so there's four possibilities now. Okay, then we compare the length of the side opposite that we have to the side adjacent, and we see it's less than the adjacent side. So that narrows it down to, that eliminates one possibility, the possibility we had in the previous problem. So now there's three possibilities left. Okay, and so if we wanted to just go ahead and figure out which possibility we have, we could just go ahead and apply the law of sines right now and see what is sine of B equal to. Because remember, you apply with the side-side angle case, you apply the law of sines, you are going to get something, sine of B is equal to something, or sine of, not B, but not sine of, so yeah, that's what's kind of confusing. The sine of they're calling this angle B, but it's sine of the angle created between the opposite side and the side you don't know. You're going to get that, you're going to get sine of that is equal to something. Yeah, I want to make that clear. It was just a coincidence that angle B here corresponded to angle B in this table here. It's really more, it's the angle that's created between the side length opposite of the angle you know and the side length that you don't know. That's what, when you apply the law of sines to the side angle case, you're going to get sine of that angle is equal to something, and that will give you information about what case you're dealing with. And we could just go ahead and do that right now and see, like, do we get sine of that angle is equal to 1? Or do we get sine of that angle is greater than 1? Or do we get sine of that angle is something between 0 and 1? That's what we're going to, for this case, that's what we're going to get. One of those three scenarios. So, I mean, let's go ahead and do that right now. Since in the previous video, we always drew the diagram first. Let's do the law of sines first. So we've got sine of B, so sine of 72.2. Again, that notation's confusing because we're thinking angle B, but angle B is just a letter. That's not the angle we're really wanting to analyze. Over the side length opposite of that is equal to, so now we need to use this and its angle opposite, so sine of C. Sine of C is the angle that we're looking at. We're wanting to analyze here. So sine of C is equal to, let's see, 145 sine of 72.2 degrees over 78.3. Okay, so let's see. 145 times sine of 72.2 divided by 78.3. 1.7632. Okay. So we know that. Now we know that we've got there's no triangle. It's impossible. There's no triangle that could be created from this. We have that case because sine of an angle can't be greater than 1 or less than -1. So we started off with, we determined is the angle, we have obtuse or acute. We saw it was acute, so we eliminated these two possibilities. Then we compared the side length of the opposite side to the adjacent side. We saw it was less than. Well, it's greater than or equal to, so it can't be this. So it's one of these three. Then we did the law of sines and got the sine of that angle over here is equal to something. Well, it wasn't equal to 1. That eliminated that. It wasn't less than 1 or greater than 0. So all we were left with is that it must be greater than 1. It was. So we had this case. There's no triangles possible. Okay? So now we could have started by drawing the diagram and getting an estimate of what we think was going to happen. And so what we would have done is we would have said, okay, there's the side length we don't know. Okay, now let's draw. This is at about 72 degrees. Something like that. Okay, let's make this kind of long because this is the adjacent side length. So that's like 145 meters. And then now B is about 80 times 2 is 160, a little more than half as long. There we go. Now we can rotate this. And so you see, we would have guessed that we had the not possible case. And I say guessed because I didn't just take a protractor and measure 72.2. I didn't measure these distances, so it's not official. You need to do the law of sines to make it official. But our assumption would have been that we have this case. And we were right. And you can see that where this came from, it wasn't just that this side length was less than or this side length was less than this side length. That was a part of it, but it was also this large angle here that we had, right? Because we could have potentially, if we don't change these two lengths, but we lower the angle, I mean, not potentially, definitely, eventually we could have a triangle without changing these lengths. So, but the answer here is there's no solution, no triangle possible with these. If you're given these side lengths and this angle, where it's not just two side lengths, but it's the side angle case, then you can't make it. There's not possible to make a triangle. Okay, so we start where we're given two side lengths and an angle, and to me, the first thing I would think is, I hope it's the side angle side case, because then I can just use the law of cosines, nice and easy. But we see one of the side lengths is opposite the angle we know, so that means it's the side angle case, ambiguous case of law of sines. Okay. Next thing you do is you see, is the angle acute or obtuse? It's acute, so we've eliminated two of the possibilities of the six possibilities. Next, you see, compare the length of the side opposite to the side adjacent. We see it's less than the adjacent, so now we've got one of those three cases. There's three cases where the opposite side length is less than the adjacent side length. And again, I want to do this a little bit differently than how we did it in the textbook, just to show you some different perspectives. Instead of drawing the diagram first and kind of guessing what we have, we can now go straight to the law of sines and see, for those three cases, we're going to get a sign that's greater than 1, a sign that's equal to 1, or a sign that's less than 1, greater than 0. So, okay. Now, let's see. We've got sine of 38 degrees, 40 minutes. So 40 minutes is what? Is how many degrees? It's 2/3 of a degree. So let's see. 38 and 2/3 is what? What is 38 times 3? 8 times 3 is 24. 114 plus 2 is 116. So 116 thirds. Okay, over the side length. Opposite of that, 9.72. Okay, it's equal to, and then here's the adjacent side, so 11.8. And then we are dealing with and then opposite that is sine of B. That's the angle of interest. Okay, so we can see that sine of B is going to be equal to 11.8 sine of 116 divided by 3 degrees over 9.72. Okay, so we're in degree mode. 11.8 times sine of 116 over 3. Okay, so we've got the 0.758. So okay, so we've got the case that we had in the opening problem. There's going to be one triangle possible here. So, okay, let's see. We've got the inverse sine. So, okay, we don't have there was 3 cases left. We don't have the no triangle possible case. We don't have the right triangle case. That would be when sine of B is equal to 1. This is the case where we've got two triangles. The case where there's only one time where you could have 2 triangles. That's when the acute angle opposite side length is less than the adjacent side length, and then the sine of the main angle in question is between 0 and 1. It's not 1, or it's not like, there's greater than 1. Okay, and so now here, what's going to happen is, we did the inverse sine and we got this. Now we think about the other angle that we just took the inverse sine of both sides. So we think about the other angle that satisfies this criteria in the second quadrant, 180 minus this. Okay, so there's these 2 angles here. So 49.3 and 130.7. What's going to happen here is that when we add this to, say, 130 plus 116 divided by 3, that's not greater than or equal to 180. So this is we can just eliminate this, and that's what happens. So there's 2 triangles, and we can go to the diagram and see. So here's the case that we have. We just did A plus B2 and saw that it was less than 180. So here are the 2 triangles. We're going to have, there's one triangle, and with angle B2, and then there's another triangle with angle B1. So what we need to do is draw these 2 triangles. So, okay, and we can see what, if we real quick do the diagram. So we draw the side length that we don't know, then we measure out, so about 38 degrees, there's about 45, somewhere in there. Okay, then this side length is a little bit less than this, like right there, but it's not too much less. That's the idea. If it was a lot less, then there's no triangle possible. If it's like a perfect amount less, then there's a right triangle possible. But if it's just a little bit less, then what happens? We rotate it. There's one triangle, the obtuse triangle, and there's the other triangle. So that's what happened. Okay, so we've got an obtuse triangle. There's one, and then we've got another something like this. I'm probably not drawing that to scale correctly, but okay, so and this is going to be, this is B2, this is B1, and then the rest are just what they were. They don't change. So A, this is still just B, and then let's see, C, C, right? Everything's going to be the same except these two different angles. So, yeah, we can see we've got B2, or let's start with B1 is 49.3 degrees, and B2 is 130.7 degrees. And then now we just need, or no, we're also going to have a C1 and a C2. A C1 and a C2. Yeah, because the way it's kind of confusing. They say that they just call this C here because they're talking about this entire angle is C. But if you look, you really do have a C1 and so this is going to be, or this could be C2, and then this is going to be C1. Yeah, so it's kind of confusing. But then you can see B is always B for both triangles. And then A is just, these are both A as well. This is just pivoted, right? This side length is pivoted. So, okay, so we've got, let's see, C1 is going to be, so let's see, we can use B1. So 49.3 plus 116 divided by 3. And then 180 minus that is going to be C1. So 92 degrees. Now C2 is just going to be 130.7. This here, 180 minus this. 10.7 degrees. Okay. So now we just need side length C. So we could do the law of sines on either one of these triangles. So, okay, sine of 116 divided by 3 degrees over 9.72 is equal to, and just pick C1 or C2. Let's do C1. So sine of 92 degrees over side length C. So side length C is equal to 9.72 sine of 92 degrees over sine of 116 divided by 3 degrees. So C is equal to, all right, 9.72 times sine of 92 divided by sine of 116 divided by 3. 15.5 meters. And there you go. Now that's the final answer. There's two triangles here. Now remember though that we did work example problems in the previous section where, like, it's not like you might have a situation where, like, there's like an actual physical scenario you're analyzing, a design scenario or something, and so you can look at your design scenario and see, well, okay, these are two possible triangles, but there's no way I could use this triangle. There's no way this triangle would work for the certain scenario that I'm looking at. So it's okay to look at your design and decide to eliminate one of these triangles. That's fine. We're just trying to, in this section, we're just trying to look at this from just the pure general standpoint. But, like, you know, we saw that, we saw, go look at those examples. I think we're going to work some examples in this section as well in the next video. Go watch those examples from the previous section where we did have cases where there was two possible triangles, but we saw from the setup of the problem that there's no way it could be one of the other triangles just because of the way, you know, we couldn't have one of the angles was clearly going to be obtuse, so we couldn't have this triangle. So, okay. And actually there is these are going to be different. This is going to be C2, this is going to be C1. So this is C1. I don't know why they This diagram is confusing. They specify B1 and B2, so why don't they put a C1 and C2? I don't know. So, yeah, you can look at it like the only parameters that are going to be consistent across both triangles are what was given in the beginning: angle A, side length B, and side length A. But the other values are going to be different. Angle C, or the angle, the angle C, the side length C, and the angle B are going to be different. So, okay, let's do once again. So sine of, we need to get C2 here divided by 9.72, and then we're going to have sine of C2, which is 10.7 degrees over C2. So C2 is 9.72 sine of 10.7 degrees over sine of 116 divided by 3 degrees. So C2 is equal to, all right, so 9.72, and then we've got divided by this, 2.89 meters. There we go. So there's the two triangles. And now I probably should have been converting these back to minutes, but you get the idea. Like I should have said, this is 49, and I guess that's going to be a third of a minute. So, but you get the idea. Okay. So we see that we've got two side lengths and an angle, and we see one of those side lengths is opposite the angle. So it's the side angle, ambiguous case of law of sines case. All right. Now, next thing we do is look and see, do we have an acute or obtuse angle? We have an obtuse angle, greater than 90. So that means that eliminates these four possibilities. We've got one of two cases. The obtuse angle case of the ambiguous case of the law of sines is pretty straightforward. We're either going to have no triangle possible or one triangle possible. And you see, we can just do the law of sines and see what sine of this angle over here is going to be. If it's greater than or equal to 1, it's no triangle. If it's between 0 and 1, it's one triangle. So we could do that, but let's go ahead and draw the diagram to see if we can guess what it's going to be. So, okay, we draw the horizontal line. Now we draw this line at about the obtuse angle, so it's just a little bit past 90. Okay. Now we analyze, we analyze the lengths between these two sides here. So the angle opposite of this angle here is, or the side length opposite of this angle here is greater than the adjacent side length. Okay, so that's going to be the case where we actually can make a triangle, because if it was less than or equal to, you can't make a triangle, right? But since it's greater than, we can make a triangle. So it looks like it's not quite double, but somewhere in there maybe, so something like that. So that's side length A, this is angle B, this is angle C. Okay. So, yeah, now what we do is we apply the law of sines. So sine of 96.80 degrees over 5.818 is equal to, and we're going to have to use this angle because we have this side length, over 3.589. Okay, so 5.818 sine of B is equal to 3.589 sine of 96.80 degrees. So sine of B is equal to 3.589 sine of 96.80 degrees over 5.818. So taking the inverse sine of both sides. Well, we're not there yet. Let's see what we get Yeah, I don't want. Let me not go too far. What is sine of b? Let's analyze what sine of b is. We believe it's going to be something between 0 and 1, but we can't say for sure because I didn't draw this like perfectly to scale. Maybe I didn't draw it right. Maybe if we get sine of b is greater than 1, then there's actually no triangle possible. Well, no, actually I take that back. This isn't about, we know it's going to be between 0 and 1 because this isn't about drawing anything. We saw this is greater than this. So 100% it's going to be between 0 and 1. So there are some cases that where you can't say for sure if you, because we can't know with some cases where it was like you know that this side length is less than this side length, but do you have the 90-degree case? What exact case do you have? It's hard to say for sure. So you need to do the law of sines to validate. But here it's going to be less than 1. So 3.589 sine of 96.8 divided by 5.818. There you go, less than 1. So now let's take the inverse sine of this. Okay, but now, so you might say, well, wait a minute, what about the other angle, right? Could there be two triangles? Well, no, this is going to, if you can think about it, we started with an obtuse angle. So you can't have two obtuse angles in a triangle. So we didn't even have to look. We don't even have to look at this. We know there's no way this is going to work because we know this is going to be obtuse. So there's only one possibility, 37.8 degrees. Okay, so that's angle B. Angle C, then we can get with just take this plus 96.8 and then subtract 180 from that. 45.4. Okay, so there's the angles. We've got two side lengths. Now let's get side length C. So side length C over sine of 45.4 is equal to, now we just pick any other pair, but it's good practice to pick a pair that, or use values that you're given. So we could do 5.818. It doesn't really matter though, but you know, because like with rounding and stuff, you'd rather use the values that are given instead of the intermediate ones that you calculate, but it doesn't really matter. Over, so sine of A. Okay, so side length C is equal to 5.818 sine of 45.4 over sine of 96.80 degrees. So, okay. Let's, okay, 5.818 times sine of, let me pull this 45.4 to get all the digits. Yeah, there we go. Okay, divided by sine of 96.8, we were given that. 4.17, and I'll use 3 decimal places. 4.174 feet. Okay. All right, so we've got two side lengths at an angle, but we see one of the side lengths is opposite the angle that we have, so we know we have the side angle case, ambiguous case of law of sines. Next, do we have an acute or obtuse angle? We have an acute angle, so that eliminates 2 possibilities of the 6, so we've got 4 possibilities left. Okay, which of these side lengths that we have is longer? Well, the side opposite the angle we have, or the adjacent side length, is shorter. So we've got one of the 3, we've got 3 cases left. The right triangle case, the not possible case, or the 2 triangle case. And so we can It looks like we're going to have the two triangle case because this is just a little bit shorter than this, but you never know. Depends on this angle, right, and how long these lengths are. So we can go ahead. Let's go straight to the law of sines. So sine of 39.68, so we can see which case we have, over 23.76 is equal to, and then we've got, so sine of A is the main angle we're looking at here, over 29.81. So sine of A cross multiplying is going to be 29.81 sine of 39.68 degrees over 23.76. So sine of A is equal to, okay, 29.81 times sine of 39.68 divided by 23.76. 0.801. So we've got the two triangle case. Just to show you again that, so we saw the angle that we had wasn't, we saw we had the side angle ambiguous law of sines case. That's what we saw first. So we know we have one of these six cases. We saw that the angle we had wasn't obtuse, eliminates those. We saw that the opposite side length was less than the adjacent side length, eliminates that. So we know we have one of these three, and we calculated the sine of the angle in question and saw that it was between 0 and 1. So it can't be this case because that's greater than 1. No solution. It's not. It wasn't equal to 1. Can't be this case. So we know it's the two triangle case. All right. And again, this we could have guessed this because it makes sense that you draw your adjacent side length, or your side length you don't know, horizontal. Then let's go to about 39 or 40 degrees. There's 45. There's about 40. Okay. Then we take this, and this is just a little bit smaller, not too much right there. Now we pivot. There's one triangle. There's another triangle. If it was just the case where we pivoted and we couldn't tell, maybe we got this perfect just kissing the bottom line here to where it would be a right triangle, or maybe it touches twice and we didn't know, then that's when the law of sines would help us. But here it seemed pretty clear that it was the two triangle case. So now let's take the inverse sine of both sides and get the angles, two angles. So, okay, inverse sine 53.23, and then take 180 minus that. So 53.23 degrees. That's going to be A1, and then A2 is going to be 126.77 degrees. Okay, so we've got, let's see. We've got, okay, and then so, okay, this is angle A, this is angle A. Those don't change. This length doesn't change, and this length doesn't change. But we've got, or no. This is the angle we're given. Okay, and then this length we're given, and then this length we're given. But this is going to be A2. This is going to be A1. This is going to be C1. This is going to be C2. As far as angle, then this will be lowercase c2, lowercase c1. So we've got A1, A2. Now let's see. We can get C2 and C1 easily because we say, so 39.68 plus this, and then 180 13.55 is C2. Okay, now C1, angle C1 is, we take this plus 39.68, and then 180 minus that, 87.09. Okay, now we just need these two side lengths. So, okay, C1 divided by sine of 87.09 degrees is equal to, and then we'll do 23.76 divided by sine of 39.68 degrees. So C1 is equal to, we can see, is going to be 23.76 sine of 87.09 degrees over sine of 39.68 degrees. So 23.76 times sine of this angle divided by sine of 39.68. 37.16 meters. Okay. Now we've got C2 over sine of 13.55 degrees, and then use the same ratio. Or no. That's going to be, will that be the same? Yeah. 23.76 divided by sine. Yeah, because we start with both of these values. Okay, so C2 is equal to, so C2 is, so 23.76 times sine of, let's see, what is it? This angle, okay, divided by this. 8.72 meters. And there we go.